We are now going to introduce the concept of electric field intensity, and we're going to use Coulomb's law to do that. I like to view electric field intensity as just a restatement of Coulomb's law. So let's put a charge Q at the origin and some other charge at any other location in space and call it Q sub t at location R. So the force Q sub t experiences is given by Coulomb's law here. Since the charge Q is at the origin, the direction will be in the radial direction in spherical coordinates. We can think of this Q sub t as a test charge that we could put anywhere in space and probe the effect of Q on Q sub t through Coulomb's law. So for instance, I could move Q sub t over there and measure the force on it. I could move Q sub t over here and measure the force on it, and so forth. So you could map out the force Q sub t would experience anywhere in space because of the Coulombic force from our charge at the origin. Now let's take Coulomb's law and divide both sides by Q sub t. On the right-hand side, the Q sub t's will cancel, and let's rename the force on Q sub t divided by the charge Q sub t E. E is what we call the electric field intensity. And for point charge Q at the origin, here is the expression for the electric field intensity. This electric field intensity is a function in space that tells us about the influence of the charge Q at the origin. For a point charge Q at the origin, the electric field intensity has spherical symmetry. A way we will imply that three-dimensional spherical symmetry is with a figure like this one. The electric field intensity lines come out in the radial direction, and the density gets less as you get further away because of the fall off due to the 1 over r squared dependence. If we put any other charge somewhere in space, the electric field intensity will tell us the force that it will experience. So if we come in and put some charge Q at location R, then the force that Q experiences, F sub Q, is equal to Q times our electric field intensity. So multiplying our electric field intensity by Q just gives us back Coulomb's law for the force between two charges when one of the charges is at the origin. So the electric field intensity is a force per unit charge, so the units would be newtons per coulomb. Newtons per coulomb is a valid unit for the electric field intensity, but it's not the most common unit. Let's multiply newtons per coulomb by meters over meters. A newton times a meter is a force through a distance, so that's work. So newtons times meters is a joule, so we have a joule over coulombs per meter. We will shortly be introducing the concept of electrical potential difference, and the unit of electrical potential, the joule per coulomb, is renamed a volt. So a newton per coulomb is the same as a volt per meter, and volts per meter is the more common unit for the electric field intensity. We can extend this concept to define the electric field intensity caused by multiple point charges. Think of a test charge Q sub t in the presence of n other charges. We previously came up with this equation when we were talking about Coulomb's law to describe the Coulombic force on a charge due to n other charges. We will now divide both sides of this equation by our test charge Q sub t. and we have our expression for the electric field intensity at some point r due to n point charges. Since we saw that superposition holds for Coulomb's law, and since the electric field intensity is defined with Coulomb's law, superposition holds also for the electric field intensity.